Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to go over explaining how two isomers can have different properties, which one's going to boil at what temperature, or not at least what temperature, but what at a higher temperature or a lower temperature, and so on. So let's get into this. So in this question we're asked, of the following two isomers, orthodichlorobenzene and para-dichlorobenzene, which we have drawn here on the board. So this is orthochlorobenzene or dichlorobenzene. Benzene because we have a benzene ring. You identify the benzene ring by a six carbon structure, six carbon ring, and then you got these double bonds here as well. This is also has the same structure. That's the benzene ring. So if you were to get rid of these and just leave that, that would give you your benzene ring. That would be benzene. And the dichloro means that we have two chlorines attached to the benzene ring. So we have dichloro here and we have dichloro here. So the ortho and the para are telling you how those two chlorines are situated or positioned on the benzene ring with regard to each other, relative to each other. If you have ortho, that means that the two chlorides are next to each other. If you have para, that means that they are opposite of each other. There's also meta. That would mean that they would skip one. So instead of being here or here, it would be there. So we call this the one. If we number our carbons, we start with one is always going to be on where the one of your substituents are bonded to the benzene ring. So we have one, we would label this one, or maybe this one, and we would work this way. So this would be 1 and 2. So if you're on the 1 and 2 position, that would be ortho. If you're on the 1 and then the 2 and 3, 4 position, so this would be 1 and 4 position, that would be considered para. If you're at the 1 and the 3 position, so this would be 1 and 2 and 3. So if the chlorine was there, this would be the 1 and 3 position. That would be considered meta dichlorobenzene. So with regard to what the ortho and the para mean, they don't. That's really all that they mean is the positioning. Like they come from the Greek words, and so what they actually meant or what people meant by them, not so clear. Ortho means right or correct, right? So I'm not sure how that fixes. If you know the word like orthodox versus heterodox, dox referring to opinion in the Greek, ortho meaning right or correct. So if you are orthodox, then you are of the correct opinion, correct belief. If you're heterodox, then you are of the different or wrong belief, right? Para or meta, right? Para means could be mean next to, but it doesn't make sense here. Meta, if you're in the meta position, meta refers to after, right? So for you philosophers out there, Aristotle's metaphysics, right, versus Aristotle's physics, meta means after. So after, or metaphysics is after the physics. So it's basically the writing of Aristotle. They came after the physics, or beyond the physics. So, but is that what these words refer to? Not really. So for ortho, we just mean the 1 and the 2 position. For meta, we mean the 1 and the 3 position, 1 and 3. And then for para, it's the 1 and the 4 position across from each other. So if they're across from each other on the benzene ring, that's para. If they're right next to each other, that's ortho. And if you skip one and go to the next one, the 1 and the 3, that's going to be your meta position. you can think, this is probably not correct. You can think of meta as being middle, right? That might help remember. So this carbon is in the middle of these two here. So this would be ortho, meta, para. So just an explanation. I know this is kind of an aside, but I just thought I'd mention it. Okay, so we have these two isomers. We got the ortho dichlorobenzene, the para dichlorobenzene, and they're asking which would you expect to have a higher boiling point and why? So you have to remember that the boiling point of a substance is going to be related to its intermolecular forces. How strong are those forces? The stronger the forces between the molecules of a particular substance, the more energy it's going to need or be needed to separate those forces, separate the molecules, to break those intermolecular forces so that they can spread out, right? So if you're trying to boil something, right, you're trying to convert it from a liquid to a gas. You're trying to separate the particles from each other. In order to separate the particles from each other, to go from liquid to gas, you're going to need to overcome those attractive forces. You're going to need to put energy. So the amount of energy that you need to put in is going to depend on how strong those intermolecular forces are. The stronger the forces, more energy is needed to separate them, to overcome those forces. So here, when we're looking at this question, which would you expect to have a higher boiling point? Well, the boiling point is the temperature at which you get things to boil, at which point you are overcoming the attractive forces, right? So if the attractive forces are stronger, you're going to have to put more energy in and you're going to have to raise the temperature higher, right? So the higher the temperature that you need to get those to get the molecules to move away and break and become a gas, uh, that's going to be related to the strength of the intermolecular forces. So that's the stronger intermolecular forces means more energy in. So you got to increase energy, you got to raise that temperature up and to get it to boil. So if we look at here, you'll notice that you have chlorines on this side. Now carbons and hydrogens, those are pretty much nonpolar bonds, right? So if you got carbon to carbon, that's going to be a nonpolar bond. If you've got hydrogen to carbon, that's pretty much a nonpolar bond. So not very polar for the carbons and hydrogens. But chlorine is a pretty high electronegative atom compared to carbon. So this is going to be a polar bond here. So the chlorine is more highly electronegative. It's going to draw the electron density this way. This one also is going to be drawing the electron density. So if you have both chlorines on the same side, then you're going to have a part of the molecule, the side of the molecule that is more polar or more electronegative, right? So you're going to have polarity in the molecule. So this is going to attract, these two chlorines are going to attract the negative electrons to them, causing this side to have a partial negative. So let me draw that in. So this is going to have a partial negative side, which means that this side is going to have a partial positive side. So here we're going to have a polar molecule. Therefore, the predominant IMF or intermolecular force is going to be dipole-dipole. Now here you have the chlorines on opposite sides. So the dipole moment for this bond is going to be going that way. The dipole moment in this bond is going to be that way. And since they're the same atom, they have the same electronegativity, they're going to be pulling in opposite directions at the same force or same amount of dipole, right? So that means that here we have symmetry. And so the dipole moments in these two bonds are going to cancel out. The rest of the molecule, as I said before, are just nonpolar bonds. So this molecule here ends up becoming nonpolar. So there's no polarity, there's no side. One side is not going to be positive or negative. We're not going to get that distinction here. So here we have polarity. Remember the magnets, you have the sides of the magnet, you have a north pole, you have a south pole. We also refer to them as the positive pole, the negative pole. So that's why we talk about polarity. So since we have a negative side and a positive side, we have poles in our molecule. This is a polar molecule. Therefore, as I said, the predominant intermolecular force is going to be dipole. Dipole. Now remember, there is London dispersion forces here or van der Waals forces here, but the predominant force is dipole. So don't forget that there is London dispersion forces here, but the dipole is going to predominate over that. Here we don't have any polarity, so the only force acting here is your London dispersion forces, your LDF. And we know that the London dispersion forces are going to be weaker in kind compared to dipole. Now, that's given that we have pretty much the same size or same size molecule here or same molecular mass. We know that as the size of a molecule gets bigger, as its molecular weight or mass gets larger, then the strength of your LDF forces are going to get larger. But we don't have to worry about that here because these are pretty much identical in molar mass because they have the same number of atoms, the same kind of atoms. So that's not going to be a factor here. So the intermolecular forces for this isomer are going to be weaker than the dipole-dipole interactions for this isomer. So since the boiling point of a substance depends on how strong those intermolecular forces are, and we just talked about that, the stronger the intermolecular force, the more energy you need to put into it to get those molecules to separate from each other to overcome those intermolecular forces. And therefore, you're going to need to raise the temperature to a higher degree. So therefore, we would expect the polar isomer to have a higher boiling point compared to the other isomer, the para isomer, because the para isomer has weaker intermolecular forces, the LDF, and therefore you don't need as much energy to separate and overcome those LDF interactions. So you can separate them more easily. You don't need to put as much energy in, and so you don't need to raise temperatures high to get it to boil. Whereas here you're going to have stronger dipole-dipole interactions, so therefore you do need to put more energy in to get those molecules to get moving, to separate from each other, and to overcome those intermolecular forces. So my money would be on this one here. Okay, so hopefully that is clear. If you still have questions, hopefully I clarified everything. But if you have questions, then please put some comments down below. Ask me. I would be happy to answer those questions. Okay, now what about the next question? It says, if you dissolve 1 gram of each of these isomers separately in 100 grams of water. So we're going to have 2 beakers of water, and we're going to put 1 gram of the orthodichlorobenzene into 1 beaker of 100 grams of water, and then we're going to take 1 gram of the para-dichlorobenzene, and we're going to dissolve that in a different beaker with 100 grams of water. And then they're asking us which solution would have a lower freezing point and why. Okay, so here we got to think a little differently, although it's related to the same thing we were talking about with regard to a higher boiling point, and that is the intermolecular forces. But we're kind of thinking in the opposite direction now. So here, again, we're thinking about the strength of the intermolecular forces. So lowering the freezing point. So which one's going to have a lower freezing point? Think about it. It might help to think about it in the opposite direction. Instead of freezing something, you got to melt it, right? So melting and freezing is the exact same thing, but just going in opposite directions. So I'm just looking for my marker so I can fix my word here. Sorry, I'm being a little OCD. So freezing and melting happens at the same temperature. If we're thinking about water, for example, water freezes at 0 degrees Celsius and ice melts at 0 degrees Celsius. It just depends on what direction are you going. Are you heating it up or are you cooling it down? So here they're asking us with regard to cooling the substance down, but you can think about it in the same way when you're thinking about heating something up, right? So um, if you are heating something up, right? If I have an ice cube, right? Or let's say if I have a solid piece of substance and I want to melt it, the melting point is the temperature at which those intermolecular forces are being overcome so that the molecules or the particles can now kind of move around, have locomotion. They can separate from each other, they can move past each other, and they get more freedom of motion because they're overcoming those intermolecular forces. And as I said before, as you can imagine, if the intermolecular forces are quite strong, then it's going to take more energy to get those molecules to move and overcome those intermolecular forces, right? So therefore, in order to melt that substance, you'd have to put more energy in. You have to raise the temperature more, right, to get it to melt because the intermolecular forces are stronger. If you have relatively weak intermolecular forces, then you don't have to put in as much energy to get those particles to move past each other to start to overcome those intermolecular forces and get them to get more freedom of motion, right? So that's in terms of melting, right? So in that regard, it's the same as boiling, right? So the stronger the intermolecular force is, the more energy you need to put in, the higher you need to raise the temperature in order to get the substance to boil as well as melt. So it works the same way. Now, what if we're working in the opposite direction? Well, the same thing applies. So again, if I'm going from liquid to solid, right? If I'm going to freeze it, I got to lower the temperature. Well, what if the intermolecular forces are quite strong, right? Those intermolecular, if the intermolecular forces are quite strong, then they want to get together. They're going to be attracted to each other more strongly, so they're going to easily come together at higher temperatures. You don't have to lower the temperature so low. You don't have to slow them down as much before the intermolecular forces kick in and attract them and bring them together, right? So if the particles are moving around really fast, the reason that you're lowering the temperature is to slow them down. Remember, temperature is related to the average kinetic energy, which is related to the average speed of the molecules, right? So if you lower the temperature, you're lowering their speed. And if you can get them to go slow enough, then the attractive forces can take over and connect them together, bring them together, and you get a phase change from liquid to solid or gas to liquid, right? So if those forces are already quite strong, right, then you don't need to slow the molecules as much or the particles as much, right, in order to allow for the intermolecular forces to start to attract and bring the molecules together. So you don't have to lower the temperature as much. So you're going to have a higher melting point or a higher boiling point if your intermolecular forces are quite strong. However, if your intermolecular forces are quite weak, like for example in your LDF, those are quite weak, relatively speaking, um, then in order to get those particles to actually attract each other and form a liquid, right, or form a solid, if we're trying to freeze it, right, if we're trying to freeze it, we want it to bring it a solid. In order to do that, then what you're going to have to do is you're going to have to slow those molecules even more in order for those weak attractive forces to start to attract and pull on the molecules or neighboring molecules, right? So if you got very weak attractive forces, then the movement of those particles is going to overcome. It's not going to allow the attractive forces to kind of bring them together. So you got to slow them down even more until they slow down so that those attractive forces now can attract the molecules, allow the molecules to attract each other, form a liquid, form a solid, right? So here in answering this question, we were looking for the one with the lower freezing point is going to be the one with the weaker attractive forces, because you got to slow those molecules down even more. You got to take away more of that energy in order to slow them down so that the weak intermolecular forces can actually do their thing and bring them together. So the answer here would be for the paradichlorobenzene would have the lower the lower freezing point in this case. So that is how you would explain which one has the lower freezing point and which one has the higher boiling point. And it all has to do with the strength of those intermolecular forces for each of the substances. I hope this is helpful. If you enjoyed this video, then please, by all means, like the video, share the video, help me out here, subscribe to my channel, hit that notification bell somewhere up there. When you do that, make sure you click all so you can be notified by all the videos I put out. And finally, put a comment down in the comment section right down there somewhere below. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question that you need help with, or a problem that you need me to help you solve, or if you have a topic you want me to cover, please put that down below. I would love to help you with that. Thanks for joining me, and have a great day.